Good afternoon,
My name is Alex,
and I'm Toby.
and this is our Energy Harvester project for ME 1222. Lucy is a busy student stressed about 4 tough exams in the upcoming week. She's consumed not one, not two, but 3 monsters in the past 5 hours and yearns for more. To top it all off, she is in PFT, the coldest building on campus.
All this caffeine consumption creates pent-up energy in her leg. Energy is then wasted when she bounces her foot anxiously. Our project concentrates on how to put this wasteful energy to good use.
In order to do this, we considered the following customer requests.
The product should be affordable to make and affordable for the customer.
The customer should feel comfortable while using our product.
The product should not affect the customer's normal behavior, which in this case is bouncing her foot.
And finally, the product should harvest energy.
In order to finalize how our customers' needs could be met, we use the following useful design tools.
One of the first design tools we used was our Gantt chart. This helped us plan our semester timeline, break the project into smaller tasks, and assign responsibilities to each team member. By organizing every major milestone, we made sure our work stayed on track and was buildable by our October deadline.
Now we move on to the House of Quality. This helped us translate customer needs into engineering specifications. By scoring how strongly each customer requirement connected to each technical constraint, we compared multiple existing products and identified which technical features mattered the most to our design, which was mainly safety, affordability, and its ability to harvest mechanical energy.
Another tool we incorporated was the objective tree. This allowed us to take broad customer goals such as safety, cost effectiveness, and overall efficiency and break them down into more specific, measurable objectives. This helped us stay grounded in what the customer truly valued throughout the design process.
And lastly, we used the comparison chart. This was used to evaluate our different concept ideas, such as the zipper-activated piezo strip, the foot pedal, the retractable ID reel, piezo dance floor, piezo weight grip, and piezo shoe insert. By comparing each concept against our criteria with pluses and minuses, we objectively determined which idea best met customer expectations. This is how we ultimately selected our strongest concept, the foot pedal.
Now that we've shown the tools we used to narrow down our ideas, we wanted to explain how we interpreted those results and how our final concept started to take shape. One of the earliest ideas we explored was a simple foot-activated pedal connected to the piezoelectric pads. In this sketch right here, our initial idea focused on applying force through the toe, since that just seemed like the most logical place to press down onto these pads.
Here also in our sketch, we have different components associated with the mechanism that we would create. We have the hinges that this pedal will be rotating about, but in order to transfer the pressure from your foot, you'd have a spring connected to a base, which would then apply pressure to the piezoelectric discs. Then a voltage spike would be created, which would power a small LED light showing the um, transfer of or the conversion from wasted energy to useful energy. Here we also have estimated costs for what this mechanism would take if we were to produce it. We have from the piezo pads to the pedal and then to the circuit components like the rectifier, the capacitor, and the wires. Also, as we continued prototyping, we realized that using the toe wasn't going to be the most natural motion for the user. When someone is bouncing their leg, like our stressed student Lucy from earlier, their heel actually makes the most consistent contact with the floor.
Right. So we revisited our drawings and shifted the force application point towards the heel. That change made a big difference. The heel provides a larger, more stable surface area and doesn't require the user to change their posture or strain their leg. Instead of asking them to push down deliberately, we designed the pedal so it captures the motion they're already doing unconsciously.
This evolution from the toe-based pressing to the heel-driven energy harvesting helped us create a design that's both comfortable and efficient. It maintains the customer's requirement of no major behavior change while improving stability and power output at the same time.
After figuring out that a heel activated pedal was the best concept and the most natural motion, we have then moved from the ideate process to now the prototyping. We began developing the physical mechanism itself.
Initially, we wanted to use springs to maintain the pressure application of the pedal towards the piezoelectric discs. But since no springs were provided by our professor and as part of the given materials in class, we adapted the design to use these binder clips that we found lying around. Um, the binder clips acted as our hinge mechanism and also as a stable way of applying the pressure. Our design process centered heavily around these binder clips that our professor provided. These clips became the foundation of our early prototypes because they were sturdy, lightweight, and already behaved like small mechanical hinges.
At first, our plan was to build most of the structure using only the provided material while 3D printing only the pedal surface. As we started iterating, we realized that keeping the pressure applying mechanism separate from the pedal created stability and alignment issues.
We had to consolidate the components in order to make it more efficient for building. Doing this helped us build it in time and make our deadline, which was mid-October, because we didn't have so many pieces to assemble. So we redesigned the entire top mechanism into a single 3D printed piece. This combined both the pressure applier and the foot pedal itself. So while before we had a 3D printed foot pedal connecting to some form of base, connecting it to the poles, which would be wooden skewers or wooden poles, which would then connect to some base attached to the whole thing being attached to a binder clip, and then the base presses down on the piezoelectric discs. We combined the entire system into one 3D printed piece. While the cons of this was it being more expensive, we ended up spending around $47 to print the full piece, and it was a big print, and we did have some issues with printing it at the 3D printing station. But on the plus side, we didn't have to assemble so many parts, and because we were not experienced in welding and hot gluing would have been too weak, we ended up producing a more durable product, which durability is one of the most important functions of it because it has to it be able to withstand the pressure that someone applies when they're bouncing their foot naturally. The person shouldn't have to alter their movement or um make their foot press down lighter because our system is not strong enough.
So yeah, this was definitely a huge improvement because it gave just a more also like a consistent force transfer onto the piezoelectric discs, which is what we wanted. We didn't want certain piezos not getting any attention. We want all of them to be collectively there all around together. And so here we have a sketch of what our idea was for the CAD model itself. And if you see to your left of the screen, we didn't add the shoe handle part, if you will, for like a nice adjustment because we thought maybe we didn't need that friction, but in conclusion, we did.
Once the mechanical design was finalized, we assembled the full system. The pedal rotates downwards when the heel presses on it. This pushes down the integrated force applier rods onto our array of piezoelectric discs. Every heel tap compresses the discs, deforming them and creating a voltage spike, which then powers our LED lights we had provided to us.
In the process of our creation, we wired those piezoelectric pads into our circuit and connected them to an Arduino just to help regulate and display the output. When the Arduino senses the voltage produced from just stepping onto the pads, it activates small LEDs. These LEDs lighting up, showing that we're successfully converting the user's or customer's wasted leg bouncing energy into useful electrical energy. Although during the design process, or really the constructing manufacturing part, we realized a key flaw.
This key flaw was the fact that our 3D print was too heavy to stay lifted slightly off the piezoelectric discs to be able to apply that force and create that pressure and apply that pressure. So in order to solve this, we added some styrofoam and cardboard in between the binder clip hinge and the 3D print to create more distance or more leverage from the piezoelectric discs themselves and be able to apply that pressure consistently and effectively towards the LED lights.
And here is our CAD model of the prototype. The foot pedal, highlighted in yellow, is designed by Tobi, and the breadboard, highlighted in blue, is also designed by Tobi. The gray being the Arduino, the piezoelectric discs, and the binder clips were designed by me, as well as the styrofoam pad itself. Here all shows where they're all placed, so the manufacturer can know where all it should go and be assembled.
And that completes our final design. A simple heel-activated pedal rotating on a binder clip hinge, applying pressure to an array of piezoelectric discs, ultimately proving that even small unconscious movements can generate energy and be harvested for power.
In the end, our design stands out as the best solution because it meets every customer need without requiring any change in natural behavior. By using the heel as a motion people already make subconsciously, we create an energy harvester that is comfortable, intuitive, and reliable.
Our final pedal also balances efficiency and affordability and manufacturability because we were able to produce it in this mid-October with this mid-October deadline. It proves that even students with a limited budget can produce, and then it can also be produced on a larger scale. The 3D printed structure provides stability and precision. The binder clip hinge keeps the mechanism simple and durable, and the piezoelectric array delivers measurable, useful power. Altogether, our design is easy to build, easy to use, and it actually works.
And that combination, functionally, comfort, and practicality, is what makes our energy harvester the strongest and most effective design for this specific project.
And
And
thank
thank
you
you for
for
your
your time.
time.